So now in this lecture, we shall learn that how we can calculate the aerodynamic shape factor for, we can say, cantilever roofs. So the first condition, we can say, as per the AS1170 code, that is given is basically the if the span is less than 15 meters, that is this cantilever span that is less than 15 meters. In that case, a separate, we can say, values and calculations are given. And for span greater than 15 meters, basically we do need to have an understanding that that shall not be a simple static structure, that shall be a dynamic, we can say, and that shall show dynamic behavior. So in that case, we do need to calculate the C dyne, that is the dynamic coefficient as per the AS1170 part 2. So now these are the two classic examples of, we can say, cricket, or we can say any football, we can say stadium roofing structure. And stadium roofing structure is usually cantilever, so that the view for all the spectators or for all the persons that are coming to see the game, that is clear. So that is a classic example of, we can say, cantilever roof structure. So we shall discuss this in detail in this particular lecture. Now, as an engineer, or if we have already discussed a lot about the wind engineering. As an engineer, we can say that, let us suppose if we are talking about this kind of structure, this is basically the sitting stadium. Sorry, these are the seats, and usually this is the arrangement of the seats that is provided. Second thing is that in here, let us suppose this is the height of this particular uh, cantilever roof. Height needs to be considered from the lower point. That should not be considered from the higher point. So at the lower point, let us assume the height is h here. The span of the cantilever roof, let us assume that this is small d. Third thing that we need to consider here is that the inclination of the cantilever roof from the horizontal, that shall be taken as theta alpha, sorry. Yeah, so that shall be taken as alpha. So these are the three parameters that we do need to understand, that is d, alpha, and h. After that, the fourth parameter, that is the we can say length of the roof. So that also we can consider. Now, what exactly is this end, internal, end, and all these parameters? We shall also discuss that, but first just jump onto the practical example, so that while solving the example, I shall explain you all the parameters that are involved. First assumption, like we have done in the earlier lecture also, the first assumption, let us assume the span of the roof is basically 12 meters. So if this is the, we can say, cantilever roof, and this is the span, and this is basically the seating arrangement of the stadium. So the span of the roof here, this is basically 12 meters. After that, length of the roof, that is in this particular direction. So and if we draw this in plan, the span, we can say length of the roof, that is assigned as L, and that is basically 45 meters. Average height of the roof above local ground level, that can be assumed as 12 meters here. Angle of inclination of roof with alpha, let us assume it is a 6 degree. So after that, the important parameter is the value of h by d, or the ratio calculation of h by d. Here h is nothing but height of the average height of the roof, d is the span. H is also 12 meter and d is also 12 meter. So that gives us h by d value of 1.0. Now there comes the three types of calculation that we do need to consider here. One, when theta is equal to 0, when wind is striking at this particular direction, this we can say it as theta equal to 0. Second case, when wind is flowing from the backside, that is, we can say theta is equal to 180. Third case, when wind is flowing perpendicular to the we can say this particular view, in that case we can take it as theta is equal to 90 degree. So in here we can see that this is basically theta equal to 0, theta equal to 180, and across the paper towards you, that shall be theta equal to 90. So that is the first concept that we do need to understand. First concept was that these are the different parameters that we do need to find out: d, l, h, and alpha. After that, second concept, the wind shall be flowing at three directions. So we shall be considering theta equal to 0. Second case, we shall be considering theta equal to 180. Third case, we shall be considering theta equal to 90. So that is now clear to us. After that, the next concept that we do need to understand, that things, or his calculation is very easy when we're talking about theta equal to 0. So how calculation is easy? Because if the value, if the value of alpha of the roof, that is basically between -7 and +7, and we can say h by d value that is less than or equal to 1.4, these are the 8 coefficients that we do need to take. So these are the 8 coefficients that has been taken also here. So after that, when we're talking about the upward loading and downward loading, upward loading and downward loading means that when we're talking about the wind, we are always talking about the applicability of wind across the structure and along the structure. We are talking about the wind applicability at end part also and internal part also. So let us suppose this is the internal part and this is the end part here. But what is internal, what is end part, and what is upward, what is downward, that all depends on the uh, direction of the wind loading. So upward loading is different when we're talking about theta equal to 0. Upward loading is different when we're talking about theta equal to 90 and when we're talking about theta equal to 180. So when we are talking about this particular case, that is theta equal to 0, I won't be mixing another concept because this is a very important case and we do need to have focus on this particular case first of all. That is when theta equal to 0. So in this case, let us suppose this is the roofing arrangement, and when wind is flowing from the front, that is theta equal to 0. So let us just have this visualization here, that is wind is flowing from this direction here. So in that case, the internal upward loading at front. So in here we are talking about the permutation and combination of three terms, internal and four terms we're talking about, internal and upward and downward. So we shall be mixing all of these terms. So first term shall be upward internal loading, and Cshp1 that can be named as front, and Cshp2 that can be named as rear. So in here also you can see the picture. So Cshp1 we are talking about the front, Cshp2 we are talking about the rear. Why? Because if the span of the roof is quite large, so we cannot say that wind shall be having same load on this part also and this part also. Here also you can see that it is a little bit higher and it is a little bit lower. So that is the practical application of the wind load. Coming back to the permutation combination here, internal and upward and downward. So internal upward loading at front, the value shall be -1.8. After that, we're talking about internal upward loading at rear. We're talking about the value of -1.1. So this value is also understood. This value is also understood. Third term, we are talking about upward end loading at front, value -1.3. Upward end loading at rear, value is -1.0. Say fifth case that we do need to understand, internal downward loading at front, the value is 0.25. After that, downward internal loading at rear, the value is 0.15. Downward end loading at front, 0.55. Downward end loading at rear, 0.65. So these are the different cases, or we can say 8 number of cases that can be made from table B.11. It is given on page number 87 of AS1170, and that is applicable only when alpha is between -7 and +7 degree. So this is plus value and alpha -7 comes something like this. So that can be said for, we can say, awnings, because awnings are usually, we can say, inclined at minus angle itself. So I hope the table B.11 applicability is now clear to you. that we can have 8 number of different aerodynamic shape factor coefficients for this particular theta equal to 0. So let me just show the applicability also. So this is the section through cantilevered roof for wind at theta equal to 0. So in here we are assuming that this is wind striking at theta equal to 0 degree. This is Cshp1, this is Cshp2. So after that, when we are talking about the aerodynamic shape factor for wind at theta equal to 0, so we are talking about the case where the contouring is done, or we can say 3 different types of range is given. In here you can see the value of 4 meter. In here also you can see the value of 4 meter. The remaining 37 meters, that is assigned these particular coefficients. So let us just try to understand the practical applicability of how we can apply all these coefficients uh, onto our practical structure. Yeah, so these were the values that we had calculated. So in here, when we're talking about the internal upward loading at front, so internal and or we can say end. So this is the internal part on the top, and to understand the internal part, we can simply refer to this particular arrangement here. So this is the internal part, and this is the end part. End part is nothing but d by 3. In our case, d is basically 12 meters. So d by 3 is basically 4 meters. So that is why this 4 meter number is given here. So it is basically applicable for d by 3, that is 4 meters. After that, internal upward loading at front. Yeah, one more thing. This is, let us just name it internal and end. So now when we're talking about the values here, so we're talking about the internal upward loading at front. This is the front part, because wind is basically striking from this part, and this is the rear part. So simply we can assign these values here. So in here minus 1.8, that shall be assigned here, and after that internal upward loading at rear, so minus 1.1, that can be assigned here. Second thing, we are talking about the end upward loading at front. So end upward loading minus 1.3, so that this value is also clear, and this value is also clear. After that, fourth value, and upward loading at rear, minus 1. That shall be applicable here, minus 1 and minus 1. Fifth value, internal downward loading at front. So internal downward loading at front. So this value shall be 0.25. So this on the cursor, you can simply see the value of 0.25. Sixth value, internal downward loading at rear, 0.15. So this is the highlighted value that can be considered. And downward loading at front, downward, and we can say and downward loading at front. So the value is 0.55. So this and this value that can be considered, and downward loading at rear 0.65. So this is the value 0.65 and 0.65. So this is how we can assign the coefficients as per the code. So I hope the wind applicability with theta equal to 0 is clear to you. After that, this was the easiest part, I must say, for calculating the aerodynamic shape factor for the cantilever roof. Theta equal to 180 is, we can say, a little bit difficult, and theta equal to 90, that is somewhat difficult to understand. So let us just take the thing slowly. Second thing, or the second concept for aerodynamic shift factor for wind at theta equal to 180 degree. So in here, as per the AS1170, if you refer to the, we can say, page number 87, the code is saying that to calculate that aerodynamic shape factor for wind at theta equal to 180 degree, that is from the rear side or from the back side, we do need to refer to the table B.4a. And in table B.4a, that is basically the table that is for the monoslope free roofs. Annexure is same, that is, it is given in the annexure B itself, but that is applicable for the monoslope free roof. So how we can understand that is that for theta equal to 180 and theta equal to 90, the values need to be derived from similar type of roofing structure, that is monoslope free roof. This is also more or less a monoslope free roof itself, but assuming that it is a cantilever roof. So as per the we can say aerodynamics of the wind structure, theta equal to 0, that is when wind is acting from the front, the behavior is different. But when the wind is flowing from theta equal to 180, that is from the back side, we can refer to the behavior of the monoslope free roof itself. In that case, we do need to consider the blocked under case. And why we are assuming the blocked under case? Because the values of the blocked under case are higher as compared to the empty under case. So we can say that code is going somewhat conservative by opting for blocked under case, and alpha needs to be considered as 0. In our case, alpha was we can say 6 degrees, but if we're talking about theta equal to 180, we just need to simply ignore the alpha and take alpha equal to 0 degree. So that is an important concept when we're talking about the theta equal to 180 degree case. After that, we can just simply highlight what are the cases that we do need to take. We do need to take theta equal to 180. We do need to take windward and leeward behaviors, that is CPW and CPL, and we do need to take the blocked under case. So this all narrows down to these 4 values. All the remaining values are not required in this particular case. So theta alpha we can have assume it as 0, theta we do need to assume it as 180 degree, and we do need to consider the blocked under case. So there are these 4 values that we do need to consider: -1 plus 0.4, -0.8 plus 0.4, -1 plus 0.4, and -0.8 and plus 0.4. So windward and leeward, when wind is flowing from the backside, this is basically the windward phase and this is basically the leeward phase. So that is how we can simply calculate that when we're talking about the we can say the front part. So front part is basically in our case that is basically the leeward side. This is basically the front and this is basically the rear if we're talking about the complete cantilever roof. So rear part becomes the windward side and front part becomes the leeward side. So we can simply refer to the CPL here, and CPL is basically the upward loading at sorry, if we are talking about the front part, we are talking about the leeward side. So in here we do need to take the -0.8. So front part minus 0.8 plus 0.4, and front part is basically the leeward side. So front is basically the leeward and -0.8 and plus 0.4. So this is how we can extract the values. Rear part, that is the windward side. Windward side, that is CPW. CPW -1 and plus 0.4, that is -1 and plus 0.4. So this is how we do need to have a clear understanding of the wind engineering itself before to extract the values of these kind of coefficients. So I hope these values are now clear to you. Let us just take the snapshot again of this table and understand the practical applicability of this in the form of a we can say diagram. So in here we can see that when wind is flowing from theta equal to 180, that is wind is flowing from back side. So this is the we can say windward side, this is the leeward side, but at the same time this is the front part, this is the rear part. So this is the leeward side and this is the windward side. So after that we can just simply open this table here. Let me just zoom it out. Yeah, so when we're talking about the wind flowing from this particular angle or direction, we do need to divide the whole roof into 2 parts. That is, let us suppose this is the 45 meters and this is basically 12 meters. So 6 meters by 45 meter area, that is basically the windward side. This is basically the leeward side, but at the same time this is the front part and this is the rear part. Now we can just simply open the snapshot again that we have taken. So in here we can see that the values that are given are basically this -1 and plus 0.4. So -1 and plus 0.4, these are the upward and downward loading at the rear side. So we have, as in, we can say that basically this is the rear side and this is the front side. At the same time, this is the the windward side and this is the leeward side. So we can simply -1 and plus 0.4 extracted from the rear side, and from the front side -0.8 and plus 0.4. So these are the -0.8 and plus 0.4. So I hope the concept is now clear to you. And there is one more thing that you need to understand, that when we're talking about the load cases, so the minimum values should be combined as one load case and maximum values should be combined as another load case. So we do need to take the minimum coefficient in one particular load case and maximum values in second load case. So I hope this is also clear to you. Now the third part, that is we can say a little bit confusing also, because in here when we're talking about the application, we are more or less talking about the drag effect of the wind. That is when the wind is flowing from this particular direction. So this is basically the 45 meters. This is basically we can say 12 meters. So we have understood about theta equal to 0. We have understood about theta equal to 180. Now we do need to understand about theta equal to 90 degree. So for theta equal to 90 degree, again, it is not given on the page number 87. That is the clause B.5. It again refers to the another table that is given, and that table is basically the we can say table B.4b. So the snapshot of B.4b is this particular table. So in here also, it is doing the bifurcation, or we can say it is dividing this whole 45 meter into various parts. So in our case, H is basically 12 meters. So up to 12 meter here, it shall show one kind of, we can say, values. From H to 2H, that is up to 12 to 24 meters, it shall show, we can say, this particular behavior values, and in the remaining, we can say 21 meters. Yeah, so in that particular area, it shall show third kind of, we can say, behavior. Why? Because when wind is flowing from this direction, it is a basic, classic example of wind engineering, that along the span of 45 meters, the wind load shall not be same. It shall be varying, and or we can say that it shall be decreasing in its intensity. So that is why in here, if in these particular three values, you can see that in here the value was -1.0. It reduces to -0.8 here, and it reduces to -0.4 here. So that is basically the bifurcation that we can understand, or we can just simply go to this particular diagram also. Yeah, in here. So when wind is flowing from this direction, that is theta equal to 90 degree. In here you can see that the values are -1. It reduces to -0.8 here, and it again reduces to much lesser value, that is -0.4. In here the maximum coefficient was 0.4, 0.4, but for the remaining 21 meters here, the value decreases to +0.2. So that was basically the concept. Now how we can calculate these values when we are talking about theta equal to 90 degree. So for that, basically the code is saying for up to 1H, the table B.4a needs to be referred with CPW values and alpha equal to 0. And for 1H to 2H, CPL values needs to be referred for alpha equal to 0. Now let us just open, we can say, table B.4a. So this was the table B.4a. So in here we do need to compare, we can say, three different we can say considerations. First consideration is that x equal to 1H, that is x equal to 12 meter. So this line is now clear to you, that upward loading from 0 to 12 meters. For that, we do need to refer to the values given for CPW in table B.4a. So when we are talking about the aerodynamic shape factor with wind at theta equal to 90 degree, we do need to refer to the table B.4b. And table B.4b, basically it again refers to the table B.4a. So so first of all, we do need to consider the the easiest or extract the easiest value. So the basic value that is given is that for x greater than 2h, that is from 24 to 45 meters. We can simply refer to the values as minus 0.2, minus 0.4 and plus 0.2 for blocked under case, as in our stadium case, because we consider it as blocked under. So we can simply refer to minus 0.4 and plus 0.2. So these two values are understood. Now these four values needs to be calculated. So for these four values, you need to understand that for x less than or equal to 1h, that is in our case x less than 12 meters, and from 12 to 24 meters, we do need to refer to the table B.4a. So table B.4a has been extracted here, and we do need to consider for alpha equal to 0. So we could just simply the cross out the wrong values here, or not required values here. So alpha shall be 0, so this shall not be considered, or we can say that we shall simply cross out all the values that are given here. Why I'm doing this, it is because it is a little bit confusing, I must say. So all of these values shall not be considered. After that, blocked under case is the applicability here. So empty under values shall not be considered. See here that for x equal to 1h, that is x equal to 12 meters, we do need to refer to the CPW values. So in our case, CPW values are basically, we can say minus 1 and plus 0.4. So minus 1 and plus 0.4. So these two values are also understood. After that, for up to 12 to 24 meters, we do need to refer to the CPL values. So CPL values, here we can see that minus 0.8 and plus 0.4. So minus 0.8 and plus 0.4. So this is how we can simply calculate the values for theta equal to 90 degree also. And when we're talking about the practical diagram here, that is the load application diagram. So these are the values. So minus 1 plus 0.4, minus 0.8 and plus 0.4, minus 0.4 and plus 0.2. So this we have simply calculated from B.4b, and the values that is between for x greater than or equal to 2h. So this is between 1h and 2h, and this is for x less than or equal to 1h. So this is taken from table B.4a, and for windward side, this is also taken from B.4a for, we can say, CPL, that is leeward side, and this is taken from the this particular table itself, that is table B.4b, x greater than 2h. So I hope the practical application is now clear to you, that how you can calculate the aerodynamic shape factor coefficient and how you can apply that for theta equal to 0, theta equal to 180, and theta equal to 90. 0 degree, it is very simple. 180 little bit complicated. 90 degree, we can say much more complicated. So now we are completed with the theoretical part. What about the practical part? As per my experience with, we can say, stadium structures, more or less we do need to do the wind tunnel testing. Why? Because the cases that are given in the code, that is more or less a theoretical case, but in practical applicability in many stadiums, we can say the stadium is curved, and the roofing itself, that is also very, we can say, very having very large parameter, and there is an opening also here. So there is a very high chance that wind pressure is like very high along the, or in these two particular bays where there is an opening. So all those cases needs to be understood either by doing CFD analysis, that is computational fluid dynamic analysis, or wind tunnel testing. In majority of the cases that or the projects that I have ended, more or less the project goes in the wind tunnel testing stage itself. So if we're talking about very large cricket stadiums such as Melbourne Cricket Ground, so if you have to design a stadium as large as that particular stadium, we more or less need to take the support of wind tunnel testing. One more reason why I do prefer to adopt for wind tunnel testing for these kind of huge projects is that it helps us save money also, and at the same time have a confidence that whatever values we are considering is are realistic values. How we can save money is that because the values of the coefficient given in code are a little bit conservative. That is my point of view again. Uh, that are a little bit conservative because they are averaged over the large we can say sample calculations, and as a simple understanding, we can say that the coefficient that are applicable on 10-meter span that are also applicable on 14-meter span as per the code. So more or less we can see that the averaging is done, and that averaging is usually done on the higher side itself, so that at any stage there is no as such risk of we can say structural failure. So that is why if we are referring to the wind tunnel testing, we do have values that are a little bit lesser as compared to the values that are given in the code. Why? As I said, code values are averaged and a little bit conservative as compared to the practical values. So that is how we can save some money by applying a little bit lesser wind load. And these values that we have calculated that are applicable for the main frame structure itself. That is, if we are talking about the picture here on the top. So if we want to design this particular truss, so the values that we have calculated that can be used to design this particular steel portal frame or truss frame, whatever we are considering. But if we want to design these purlins, or if we want to design these sheetings or fixing arrangement, that can be done only by considering the local coefficients. So that can be calculated by considering the local coefficient. So that is the thing that you do need to understand. So I hope the concept is now clear to you, that how we can calculate the static aerodynamic shape coefficient for cantilevered roofs and canopies. Now in the next lecture we shall learn that how we can calculate the dynamic response for cantilever spans greater than 15-meter span.